a ship's bow, folded downward like wet cardboard. Steel, not metaphor, the Norwegian vessel Wilstar, May 1974, in the Agulhas current. 6 years earlier, the tanker World Glory broke in half on this coast. 10 of her 34 crew survived. This is the water off Cape Agulhas, 34 degrees 50 south, where the Atlantic and Indian Oceans officially meet. The easy answer is a Southern Ocean swell hitting a 5-knot current head-on. True and almost useless. The wave is not the trap, the shape of it is. Why do seas here hit harder than the wind allows? Now ask 1815, because 1815 is where the pattern starts, and the pattern is the point. Not one bad night, not one unlucky ship. A physical arrangement of land, water, wind, and depth that has been sitting off the southern tip of Africa for as long as anyone has been sailing past it, waiting for the same 3 or 4 conditions to line up, and then doing the same thing to whoever happens to be there. Wooden East India men, iron paddle steamers, 258,000-ton supertankers on their maiden voyage. The hull material changes. The mechanism does not. Start with the place itself, because almost everything people assume about it is wrong. Cape Agulhas sits at 34 degrees, 49 minutes, 59.6 seconds south, 20 degrees east, about 170 kilometers southeast of Cape Town in a region called the Overberg. It is the southernmost point of the African continent, and the International Hydrographic Organization uses it as the official dividing line between the Atlantic and the Indian Ocean. There is a marker there. Tourists photograph it. 2 oceans, 1 stone plinth, 1 line on a chart. Now here is the first thing that should bother you. If you were standing on the deck of a ship a few miles offshore, looking north at the southern end of Africa, you would very likely not know you were looking at it. Cape Point further west is theatrical. Cliffs, a spine of rock, a lighthouse high enough to be seen from a long way out. Sailors have used it as a landmark for 5 centuries because it announces itself. Cape Agulhas announces nothing. The coastline there is low, flat, and featureless, a gradually curving shore of rock shelf and sand, backed by scrub and limestone flats that barely rise. The rock is Table Mountain Group sandstone and quartzite, the same family of stone that makes Table Mountain and Cape Point dramatic, but here it lies almost horizontal and hardly lifts above sea level. From seaward, in poor light, in rain, in the ordinary gray murk of a passing cold front. The southern tip of Africa looks like nothing at all. It looks like a slightly darker line where the water stops. And out in front of that low, quiet-looking shore, the rock keeps going. Reefs and drying rocks extend offshore in a scatter that has been killing ships for 3.5 centuries. The Bredasdorp Shipwreck Museum, which exists specifically because of this stretch of coast, tells the stories of roughly 150 vessels lost here. Other counts put the number of wrecks along the southern Cape shore since the 1670s at around 130. Some local estimates go past 200. Take the lowest of those figures, and it is still one of the densest concentrations of shipwreck anywhere on the continent. The counting starts in 1673, and the first entry sets the template for everything after it. On the 23rd of August that year, a Dutch East India Company ship called the Zoetendaal, 448 tons, homeward bound from Batavia with a cargo of rice, went ashore on the coast near Cape Agulhas. She is the oldest recorded shipwreck on the South African coast. What her survivors did next is the detail worth keeping. They came out of the surf onto an empty shore with no idea where they were, and they started walking toward the Cape. About 3 hours later, they came on a large freshwater lake that nobody in Europe knew existed. They named it after their ship. It is still called Zoetendaal, and it is still there, a few kilometers inland from the beach that wrecked them. 3 hours of walking to water. That is the measure of this coast in 1673. Not a rescue, not a settlement, not a signal. Just how long you have to walk before the land gives you something. There were people here, of course. The southern Cape Coast has been inhabited for a very long time, and the communities that grew up along this shore did something that every passing ship failed to do. They learned it. Go to Struisbaai today, 4 kilometers from the Cape, or to the village now called Arniston a short way east, and there is a working fishing fleet on the beach that has been reading this water for generations. The boats are called chukkies, small wooden-decked line boats, diesel-engined now, built for exactly this shore. The steering arrangement tells you what they were designed against: a wooden plank attached to the rudder, worked with the operator's feet, so the man's hands stay free and he can steer the boat through an oncoming swell with his legs while working. Not folklore. An engineering response to a specific sea state, worked out by people who go into it and come back. Struisbaai, Arniston, and Kalk Bay are now among the last places in South Africa where traditional fishing boats still put to sea daily. And the phrase attached to that in every description of them is the important one: weather permitting. The fleet at Struisbaai has no schedule imposed from outside. There is no charterer in Rotterdam and no delivery window. When the swell is wrong, the boats stay on the beach, and the men who own them lose a day's income and accept it, because the alternative is a category of loss they cannot absorb. Motorization arrived here late. The first motorized boats around 1920, a harbor at Arniston in 1936, the Struisbaai harbor not until 1959 and expanded in 1990. And even with engines, the operating rule did not change. Knowing when not to go is the skill. Every disaster in this story involves somebody who could not apply that rule. A troop ship carrying wounded men home, a tanker on charter, a trawler with a season to work, a cruise ship with a sailing time printed on a ticket. So the tip of Africa is hard to see and hard to approach. That would be enough of a problem on its own. It is not the problem. It is the setup for the problem. Here is the detail that gives the place its name, and it is a genuinely strange one. Portuguese navigators rounding southern Africa around the year 1500 noticed something in this longitude that must have felt close to a gift. The compass needle pointed at true north. Magnetic declination. The angle between where the needle points and where the pole actually is was effectively zero here. The needle and the world agreed. They named it Cabo das Agulhas, Cape of Needles. Think about what that meant to a navigator with no chronometer, no radio, no satellite, and no reliable way of fixing longitude. It meant a place on the planet where your most important instrument stopped lying to you. It was briefly the most trustworthy piece of ocean on the route to India. That is gone. The magnetic pole wanders, and it has wandered a long way in 500 years. The needle no longer agrees with true north anywhere near Cape Agulhas. Every modern chart of these waters carries a substantial westerly correction that a navigator must apply. The name is now a fossil. It records a condition that stopped being true centuries ago. On a headland, you cannot reliably see. In front of a shelf, you cannot see at all. Watch for that shape, because it repeats. This coast keeps handing people a reason to be confident, and then quietly taking it back. Which brings us to a ship that had every reason to believe she was already past. The Arniston was a British East Indiaman, chartered by the government as a troop ship, and in the spring of 1815, she was doing one of the more decent jobs a ship could do: carrying wounded soldiers home. She had left Ceylon on the 4th of April with men invalided out of the Kandyan Wars, bound for England. There were something in the order of 378 people aboard, including 14 women and 25 children. She was not alone. She sailed in a convoy of East Indiamen, escorted by 2 Royal Navy ships, HMS Africaine and HMS Victor, and that arrangement mattered more than it sounds. Convoy ships signaled their positions to each other daily. The Arniston's master, Captain George Simpson, could take his longitude from the other ships, because he did not have the means to work it out himself. The Arniston had no marine chronometer. That single missing instrument is the whole story, and the reason it was missing is worth sitting with. A chronometer cost somewhere between 60 and 100 guineas. Simpson could not afford one out of his own pocket. The ship's owners would not buy one. According to the account, when he pressed the point, they let him know that another master could be found who would sail without one. So he sailed without one. A commercial decision taken by people who were never going to be aboard, about an instrument whose entire purpose is to tell you where you are on an east-west line off a coast that runs east to west. On the 26th of May, in bad weather, the Arniston damaged her sails and fell out of the convoy. The escorts and the other Indiamen went on. With them went the daily longitude signals. From that moment, Simpson was navigating by dead reckoning alone, estimating his position from course, speed, and time, with the accumulated error of days of storm-driven sailing baked into every figure. At 7 in the morning on the 29th of May, land was sighted to the north. Now put yourself in that moment, because this is where the geography does its work. Simpson believed, from his reckoning, that he had run far enough west to be off the Cape of Good Hope. Land to the north, at that longitude, would be the Cape Peninsula. His reckoning put him roughly 100 miles west of the Cape of Good Hope. He was in fact east of it, looking at Cape Agulhas, a low, flat, unremarkable shore, with nothing on it to contradict him. There is no silhouette here to say you are wrong. Cape Point would have argued with him. Agulhas simply agreed. There was a way to check. The Arniston was floating above one of the broadest shallow shelves in the southern hemisphere, and a sounding line dropped over the side would have found bottom at depths that made no sense off the Cape Peninsula. Simpson did not sound. At 4:30 that afternoon, on the strength of a landfall he had misidentified, he altered course to the north to run for St. Helena. He was now steering a ship into a bay. Weather closed in overnight and worsened through the 30th. By the afternoon, the Arniston was embayed on a lee shore in a storm. Being driven onto a coast she was not supposed to be anywhere near. They tried the one thing left. They anchored. Anchoring a heavily laden East Indiaman on an open coast in a gale is an act of desperation, and it is also the correct act. If the ground holds, the ship stops moving toward the rocks, and you buy hours. The anchors would not hold her. She kept dragging toward the reef at Van Huyskrantz, and everyone on that quarterdeck could watch it happening. That was the last option gone. Around 4 in the afternoon, Lieutenant Bryce, one of the military officers aboard, went to Simpson and made the argument that experienced men make when they know the ship is already lost. Run her aground deliberately, in the best place available, while you can still choose the place. Deliberate grounding is not surrender. It is the last decision you get to make with any control in it. Simpson did not take it, or did not take it in time. At about 8 that evening, the Arniston struck rocks half a mile from shore. Accounts disagree on how much of that interval was hesitation, and how much was a ship that could no longer be steered anywhere at all. Half a mile. In good weather, that is a swim for a strong man. In a storm, on a shelving rock bottom, with breaking surf between the wreck and the beach, it is a distance most people aboard will never cross. She heeled over into the wind. The crew tried to right her by cutting away the guns on the high side to shift weight. A real, physical, sensible attempt to give her a chance, made by men standing on a sloping deck in the dark with axes. It did not work. The sea began taking her apart where she lay. 372 people died. Captain Simpson died. Lieutenant Bryce, who had argued for the beaching, died. So did the 6th Viscount Molesworth and his wife, and 4 sons of Colonel Andrew Giles of the 73rd Regiment, Thomas, William Noble, Andrew, and Alexander McGregor Murray. Their mother later put up a memorial with their names and ages on it, and it is still there. 6 men reached the beach: the boatswain, Dr. Gunter; the carpenter, John Barrett; the carpenter's mate, Charles Stewart Scott; and 3 seamen recorded as Grung, Gibbs, and Robinson. They got through the surf by the account, only with great difficulty. And then the coast did the thing it had done to their captain. It lied to them by omission. The 6 survivors buried what bodies they found on the beach and then set off walking east because they believed, reasonably, on the same misapprehension that had wrecked the ship, that Cape Town lay in that direction. It did not. Cape Town lay behind them, to the west. They walked for 4.5 days into empty country, worked out that they were wrong, and walked back to the wreck. There they lived off a cask of oatmeal that had washed ashore and started trying to repair the ship's pinnace, which is an extraordinary thing to attempt with a carpenter, a carpenter's mate, and hand tools on an open beach. Nobody was looking for them. Nobody knew they were there. There was no signal to send and nothing to send it with. On the 14th of June, 6 days after they got back to the wreck, and more than a fortnight after the ship struck, a farmer's son out shooting found them. That is what rescue looked like on this coast in 1815. Not a lifeboat, not a station, not a search. A teenager with a gun by chance, 16 days late. The village nearest the wreck was called Van Huiskrans. It is now called Arniston because after that night nobody could talk about the place without talking about the ship. In 1982, students from the University of Cape Town carried out an archaeological survey of the wreck site, and the material they recovered is in the Bredasdorp Museum. You can go and look at it. The Arniston proves something less obvious than a captain making a mistake. It proves how short the interval is on this coast between an error and its consequence. Simpson misidentified that landfall shortly after dawn on the 29th. The ship struck at 8 in the evening on the 30th. Something like 37 hours, separated a wrong guess about longitude from 372 deaths. And for most of that time, the ship was sailing normally in company with nothing, under a captain who believed he was doing exactly the right thing. There was no moment of recklessness to point at. There was a missing instrument, a lost convoy, a shoreline with no features, and a bay shaped to catch anyone who turned north too soon. The response to that was the obvious one, and it was a good one. Build a light. Construction of the Cape Agulhas lighthouse began in 1847 and finished in 1848, and the light first burned on the 1st of March, 1849. It was built of local limestone, modeled loosely on the ancient Pharos of Alexandria, and it is the second oldest working lighthouse in South Africa, still operating today, declared a national monument in 1973. The Arniston disaster is one of the wrecks explicitly credited with pushing the colonial authorities into building it. A lighthouse solves a specific problem with real precision. It converts an invisible headland into a visible, identifiable, timed flash. And it does so at night, which is when the coast used to be at its most anonymous. Ships stopped mistaking Agulhas for Cape Point. That failure mode largely closed. It closed exactly one failure mode, because the thing that makes this coast dangerous was never really the headland. The headland is the last 20 meters of a hazard that starts 250 kilometers out to sea, and no light in the world reaches that far. South of Cape Agulhas, the seabed does something that no other stretch of the southern African coast does. Instead of dropping away, it stays shallow and keeps staying shallow for an absurd distance. This is the Agulhas Bank, a broad triangular platform of continental shelf that pushes roughly 250 kilometers south of the Cape before the bottom finally lets go and plunges to the abyssal plain. The numbers matter here, so translate them into something you can picture. From the shore, the bottom slopes down fairly quickly to about 50 meters. Then it more or less stops sloping. For most of the next 250 kilometers, the water is around 60 meters deep on average, gradually reaching 200 meters at the outer edge, and then it falls off a cliff, down past 1,000 meters in a very short horizontal distance, and on down to something like 1,800 meters beyond that. 60 meters of water, 160 kilometers from land. That is roughly the height of a 20-story building between the keel and the mud, over an area larger than many countries. It is a spectacular thing biologically. The Agulhas Bank is one of South Africa's great fishing grounds precisely because it is shallow, sunlit, and productive. Trawlers work it. Line boats work it. It feeds people. Dangerous places are frequently valuable for the same reasons they are dangerous. And this one is a textbook case. It is also a wave amplifier the size of a province. The chain runs like this, and it is worth walking slowly because everything later in this story is built on it. Deep in the Southern Ocean, in the belt of latitudes sailors call the Roaring Forties, low-pressure systems track east around Antarctica in an endless procession. The wind in those systems blows across open water with nothing to interrupt it, fetches of 1,000 miles and more. Wind blowing that long over that distance produces waves that are fully developed, which is a technical way of saying they have absorbed everything the wind can give them. They are big, but more importantly, they are long. Wavelengths of 200 meters and up, periods of 12 seconds and up between one crest and the next. Those waves then leave the storm and travel. Long waves travel fast and lose very little energy doing it. A 12-second swell moves across open ocean at something like 30 to 35 knots. It can outrun the storm that made it. It arrives days later under a clear sky with no wind behind it at all. A wave in deep water does not care about the bottom. The orbital motion of the water particles dies away with depth, and as a rule of thumb, it is essentially finished at a depth of about half the wavelength. So a swell 200 meters long is reaching down and stirring water 100 meters beneath the surface. In 4 kilometers of open Southern Ocean, that is nothing. Over the Agulhas Bank, in 60 meters of water, it is everything. When the bottom comes up to meet a long swell, the wave starts dragging. The base of it slows down. The top of it does not. The wave compresses lengthwise. The crests bunch closer together. And since the energy in it has to go somewhere, it goes upward. The wave gets shorter, taller, and steeper, all at once, without any additional wind. Take the same wave into shallow enough water, and the face steepens until the crest outruns its own base, and the whole thing breaks. None of that is exotic. It is the reason surf exists. What makes it dangerous here is scale. This is happening to enormous, deep-reaching Southern Ocean swell over an area 250 kilometers across, in water that is shallow enough to grip the wave, but far too deep to see the bottom or feel like a coastline. You are 100 miles from land in what looks like open ocean, and the seabed is quietly reshaping every wave that passes under you. Sailors on this coast have a name for the result: Cape Rollers. Steep, high, pyramid-shaped waves that stand up where the energy concentrates, with a bad habit of appearing in a sea state that does not otherwise justify them. Hold on to that phrase, a sea state that does not otherwise justify them. It is going to come back at the end of this story, with 2 men dead. There is a further consequence of a big shallow bank, and it is one that navigators of the sailing era understood better than most people do now. A shallow shelf is where the rocks are. Deep water is, in a crude sense, safe water. A ship with 3,000 meters under the keel cannot hit anything. A ship in 60 meters, over a rock platform that has been eroding for millions of years, in an era before systematic hydrographic survey, is moving through a minefield whose contents nobody has finished counting, which is exactly what happened to one of the most famous ships ever lost on this coast, on a night when the sea was calm. HMS Birkenhead was an iron paddle steamer, a Royal Navy troop ship, and on the 26th of February 1852 she was doing a routine and rather dull job, moving soldiers from Cape Town up the coast toward the Eastern Cape frontier for the ongoing war there. She carried something in the region of 640 people, though the exact figure has never been settled, because the ship's papers went down with her. The Times printed 643 at the time, and that number stuck. The National Army Museum gives 638. Both are estimates. Aboard were soldiers from several regiments, a number of their wives and children, ship's crew, and horses. She left Simon's Bay and steamed southeast along the coast in the dark, in fine weather, on a flat sea, making around 8 knots. Her master was hugging the coast, which was normal practice. It shortened the passage and kept the land in sight. He was doing nothing unusual, and nothing that would have raised an eyebrow on any other night. At around 2 in the morning, off Danger Point near what is now Gansby, roughly 87 miles from Cape Town, the Birkenhead ran onto a pinnacle of uncharted rock. Understand what that phrase means physically. Not a reef she scraped. A single jagged spike of stone, standing up off the shallow shelf that no survey had recorded, driven up through the bottom of an iron hull at 8 knots. It tore into the forward part of the ship and instantly opened the lower troop deck to the sea. More than 100 soldiers drowned in their hammocks without ever being properly awake. They were asleep in a compartment below the waterline, on a calm night, a long way from any help, and the water was in the space before anyone could reach the ladder. That is the first thing the Birkenhead proves, and it has nothing to do with weather. On this shelf, in this era, catastrophic damage could arrive with no warning of any kind. There was no gale to read, no barometer falling, no swell building, just a chart with a gap in it. The next 20 minutes are the reason people still know the name. The ship was mortally damaged, and everyone senior understood it within minutes. There were nowhere near enough boats. Of the boats there were, several could not be launched. Davits seized with paint and rust, tackle that would not run. 3 got away. Lieutenant Colonel Alexander Seaton of the 74th Highlanders, the senior Army officer aboard, had the soldiers formed up on deck and held them there while the women and children were put into the boats. Then, as the ship began to break, the order was given that the men should not swim for the boats, because a mass of swimmers converging on an overloaded boat capsizes it and kills everyone in it. They held. The ranks stayed on the deck while the ship went down under them. Between roughly 193 and 206 people survived, out of an estimated 640. Among them were around 113 Army personnel of all ranks, 6 Royal Marines, 54 sailors, 7 women, and 13 children. Every woman and every child aboard the ship lived. 8 of the horses swam ashore. A 9th broke a leg getting off the ship. The men in the water faced a swim of 2 to 3 miles to a coast fringed with kelp, and that stretch of shore holds one of the densest populations of great white sharks anywhere. Cornet Bond, who made the swim, described 2 men near him disappearing with a shriek, most probably taken by sharks. Others died of cold or exhaustion or could not get through the kelp. Some clung to wreckage for hours and were picked up the following day. Local people afterwards called the great whites of that coast Tommy Sharks, after the soldiers. The behavior on that deck became known as the Birkenhead Drill, and it is the origin of the Women and Children First Protocol as a formal expectation rather than an occasional act. It was cited across Europe for the rest of the century. The Prussian king reportedly had an account of it read to his regiments, and here is where you have to be honest about what that discipline actually achieved, because the sentimental version of this story quietly avoids it. The drill saved the people who could be put in the boats. It saved every woman and child. That is a real, measurable, extraordinary outcome, and the men who stood still on that deck earned every word written about them since. But roughly 450 people died anyway, and the reason they died is that a ship carrying more than 600 people had boat capacity for a fraction of them. on a shelf whose rocks had not been charted, hours from any help, at 2 in the morning. Order changed how those deaths were distributed. It could not change how many. That is the second thing the Birkenhead proves. Human discipline operates on the distribution of a disaster, not its size. Only equipment, information, and distance change the size. So the obvious answer to the Birkenhead was more information. Survey the shelf. Chart the rocks. The rock that killed her is now marked on the charts as Birkenhead Rock, and over the following decades, the Admiralty and later South African hydrographic surveys filled in a great deal of what had been blank. Which raises the question that should be nagging by now. If the coast was charted and lit, and if ships had steam engines that meant they no longer had to run before the weather, and iron hulls, and by the early 20th century, wireless telegraphy, why did ships keep disappearing here? On the 26th of July, 1909, the steamer Waratah left Durban for Cape Town with 211 people aboard. She was a new ship, a little over a year old, a large passenger and cargo liner running the Australia-South Africa-London route. She was carrying a substantial cargo, including a large tonnage of lead concentrates. And she had a reputation among some of the people who had sailed on her for being tender, for rolling slowly and hanging at the end of a roll longer than felt comfortable. That reputation is genuinely documented, and it is also genuinely disputed. Other experienced passengers and officers said she handled normally. In the early hours of the 27th, she overhauled the Clan Line steamer Clan McIntyre off the Natal coast. The two ships exchanged signals by lamp. The Waratah was the faster vessel and drew ahead, and by about 9:30 that morning, she was over the horizon. The weather that day turned severe. That evening, the liner Guelph, bound the other way for Durban, tried to exchange lamp signals with a ship in bad visibility and could only make out the last 3 letters of her name, T-A-H. Nothing after that has ever been confirmed. The Waratah did not arrive at Cape Town. 2 of the largest search efforts of the era were mounted, covering 14,000 and 15,000 nautical miles of ocean respectively, running for months. They found nothing that could be positively identified as her. No confirmed wreckage, no bodies, no survivors. A Board of Trade inquiry examined her stability and her loading and could reach no definite conclusion about what had happened to her. Claims to have located the wreck have been made more than once over the following century, including a widely reported announcement in the late 1990s. None has been confirmed as the Waratah. As of now, the ship is still missing, and anyone who tells you flatly what happened to her is guessing. That uncertainty is not a gap in this story. It is the story. Because the Waratah is the moment the old explanations run out. She was not badly navigated onto an unlit coast like the Arniston. She did not hit an uncharted rock like the Birkenhead. She was a modern steel steamer with engines on a charted, lit, well-traveled coastal route in company with other shipping. And she went from a lamp signal to nothing in a matter of hours, with 211 people aboard, in a stretch of water where ships pass every day. Something out there was capable of taking a large modern vessel apart, faster than she could report it. Nobody could say what. It took another 65 years. A professor of oceanography who had also commanded ships and a run of damaged supertankers before anyone assembled the answer. And when they did assemble it, the answer turned out to be sitting well to the northeast of the cape this story is named after, which is the first thing about Cape Agulhas that most people get wrong. The Agulhas Current is one of the largest and fastest ocean currents on the planet, and it exists because of a long chain of plumbing that starts thousands of kilometers away. Trade winds across the central Indian Ocean push a broad westward drift called the South Equatorial Current. That drift runs into the east coast of Madagascar and the coast of Mozambique in splits. One branch runs south down the Madagascar coast, The other runs south through the Mozambique Channel. Off the coast of what is now KwaZulu-Natal, somewhere between Durnford Point and Durban, the two rejoin, and from there the combined flow turns southwest and runs down the edge of Africa as a single enormous river of warm water. Estimates of how much water it moves vary with method and location, but a commonly cited figure is on the order of 70 sverdrups. One sverdrup is 1,000,000 cubic meters per second. 70 of them is a flow several hundred times the combined discharge of every river on Earth, all going the same way, all warm, all pressed against one continent. The core of it is narrow, roughly 100 kilometers wide, though it broadens considerably when you count the recirculation on its flanks. It is also deep. When J.K. Mallory examined it in the 1970s, he described a core penetrating more than 300 meters, which is the detail that determines everything about its behavior. The current is deeper than the continental shelf it runs alongside. It physically cannot climb onto the shelf and stay there. It is forced to run along the outside edge, and like every western boundary current, it accelerates where it is squeezed. Between Port St. John's and East London, Mallory recorded speeds of 4 to 5 knots just seaward of the shelf edge, with an average of 3 to 4. 4 to 5 knots does not sound frightening. Reframe it. That is a body of water more than 300 meters deep and 100 kilometers wide, moving at roughly the speed a person jogs continuously for as long as anyone has measured it. A ship steaming northeast against it at 16 knots makes 12 over the ground and burns the difference for nothing. A ship steaming southwest with it gets a free 4 knots, which is why southbound traffic uses it and has for 150 years. That free 4 knots is the bait. Now, the reversal that most people never hear, and the reason the title of this story needs unpacking rather than repeating. The stretch of ocean that has destroyed the most modern shipping is not directly off Cape Agulhas. It is upstream. Mallory was explicit about it. Every report of an abnormal wave he could find came from the coast between Durnford Point and Port Elizabeth, and the concentration was between Durban and East London. That is somewhere between 700 and 1,300 kilometers northeast of the Cape. The reason is the shape of the shelf. Off Durnford Point, the continental shelf is about 20 miles wide. Then it narrows abruptly and stays at roughly 5 miles wide all the way to Port St. John's, before gradually widening again to 20 miles off Great Fish Point. Between Port St. John's and East London, the outer slope is unusually steep. The 1,000-fathom line lies within 15 miles of the shelf edge, and the slope is cut by deep submarine canyons, whose full extent had not been mapped when Mallory wrote, because nobody had sounded outside the 200-meter line in enough detail. So on that stretch, the fastest part of the biggest current in the region is compressed into a narrow lane, hard against a steep drop-off. Within a few miles of the coast, everything happens in one place. That is the killing ground. Cape Agulhas is the other end of the same machine. Follow the current southwest, and it stays glued to the shelf edge all the way down the coast, until it reaches the tip of the Agulhas Bank, 250 kilometers south of the Cape. There, the shelf ends. The topography that has been steering the current for 2,000 kilometers simply stops, and the current's own momentum overwhelms the balance holding it to the coast. It leaves the shelf, and then it turns around. This is the Agulhas retroflexion, and it is one of the strangest features in physical oceanography. The current swings east, loops back on itself, and heads off into the southern Indian Ocean as the Agulhas return current. Most of that 70 sverdrup flow reverses direction in a bend a few hundred kilometers across. The loop is not stable. It stretches west, pinches off, and sheds enormous rotating eddies, Agulhas rings, that carry warm, salty Indian Ocean water into the South Atlantic. A typical ring is around 240 kilometers across, spins at speeds up to nearly a meter per second in its upper layers, and drifts away northwest at about 5 to 8 kilometers a day. So Cape Agulhas is not the source of the danger, it is the hinge. It is where a current that has been running in a straight line for 2,000 kilometers turns hard, sheds pieces of itself, and unloads all of that structure onto the shallowest broad shelf in the region, directly into the path of Southern Ocean swell, arriving from the southwest. Currents going one way, rings spinning, swell arriving from 1,000 miles of open Southern Ocean, 60 meters of water underneath it, and ships crossing the whole arrangement because there is no other way around Africa, which leaves one component still missing, and it is the trigger. Everything described so far is permanent. The bank is always there. The current is always running. Ships pass safely through it every day of the year. Something has to switch the system on. That something is a cold front, and the specific way this coast handles one. Mallory laid out the seasonal pattern carefully. In the southern summer, roughly November to May, a low sits over the interior of South Africa, and a high extends over the southwest Indian Ocean. So the prevailing winds on the southeast coast come from the northeast, running with the current, adding to its speed, producing nothing unusual. Southern ocean depressions in those months mostly track too far south to matter. Long swell rolls in from the southwest but arrives regular and well-behaved. In 11 years of records, Mallory found only one summer incident, the Jagersfontein, on the 18th of December 1959, and even then a very deep depression of 976 millibars had passed Marion Island 12 hours before, which is unusual for December. From late May to mid-October, the pattern changes. The interior low fills in, the southern ocean depressions push further north, and their influence reaches the entire southern and southeastern coast of the country. Cold fronts sweep up from the southwest one after another, and after each front passes, strong southwesterly winds blow parallel to the coast for 24 to 48 hours. Parallel to the coast? That word is doing a great deal of work. Mallory noticed something on the weather charts for late September 1973 that he described as possibly unique to this coastline. The isobars ran parallel to the southeast coast for days at a stretch, which means the wind blows along the coast, along the shelf edge, and directly along the axis of the Agulhas current, over exactly the strip of water where the current is fastest. Further west, the isobars curve round faster. The wind backs to the south sooner, and the current has already spread out and slowed. The alignment only works here. Now watch the 12 hours before a front, because this is the part that turns a weather system into a weapon. Before the front arrives, the wind on this coast typically blows from the northeast at force 6 or 7, sometimes for a day or more. That northeast wind does 3 separate things, and each one loads the gun. First, it blows with the current and accelerates it. Second, it pushes the surface water on the continental shelf, and because of the Coriolis effect, that water is deflected offshore. Water leaves the coast, and deeper water rises to replace it, upwelling. Anyone who has swum off this coast after a hard northeaster knows what that feels like. The sea temperature drops several degrees in a day. Third, and most importantly, all that displaced water piles up out near the 200-meter line, raising sea level there. A raised sea surface out at the shelf edge creates a pressure gradient, and that gradient makes the Agulhas current run faster still, in the exact place where it is already fastest. So by the time the front arrives, the current at the shelf edge has been deliberately spun up by the weather that preceded it. Then the front comes through, moving along the coast at around 25 knots. The wind switch is violent. Mallory's records show a change from northeast force 6 to southwest force 6 or 7 in about 4 hours. Not a gradual veer over a day. 4 hours from one direction to the opposite one, at gale strength. There is one more piece, and it is subtle. About 6 hours before the front arrives, a countercurrent begins to flow close inshore, east to northeast at 1 to 2 knots, within 3 or 4 miles of the coast, inside the southwest flowing Agulhas current. Mallory attributed it to a combination of wind-driven surface flow and ingress of the west wind drift, the retroflexion south of Mossel Bay, and a gradient set up by the falling atmospheric pressure raising mean sea level as the depression moves east. Remember that inshore counter current. It becomes the reason northbound and southbound ships end up in completely different water, and it is why one of them survives the day and the other does not. So assemble the machine. Follow it as a chain, because it is a chain and not a list. A deep low, often centered at or near Marion Island, roughly 1,000 nautical miles south-southwest of the coast, drives southwesterly winds across the Southern Ocean with a fetch of 600 to 1,200 miles for 24 hours or more. That produces a fully developed sea out there, a significant wave height of at least 6 meters, isolated maxima around 9, wavelengths around 210 meters, period 12 seconds. Those waves travel northeast at 30 to 35 knots and arrive on the South African coast still long, still powerful, hours or days ahead of the weather that made them. Then the front reaches the coast and the wind flips to southwest. Within 1 hour of the switch, locally generated waves reach around 3 meters, with a short wavelength of about 60 meters and a period of 6 to 7 seconds. Short, steep, ugly wind sea on top of the long ocean swell. Now both wave systems run into a current going the other way at 4 to 5 knots. A wave moving against a current gets compressed. The current is dragging the water backwards underneath it, so the wave's forward progress relative to the ground slows, the crests bunch closer together, and the energy that was spread along a long wavelength gets packed into a shorter one. Same energy, less length, so more height. Mallory calculated it. The 3-meter local wind sea on a 60-meter wavelength becomes 4 meters or more on a wavelength of about 53 meters. The 6-meter Southern Ocean swell, slowed on arrival at the current, gains roughly 25% in height, up to about 8 meters, on a wavelength squeezed from over 200 meters to around 150. That alone would make for a savage sea. It is not the killer. The killer is that these are two different wave systems, with different wavelengths and different periods running through each other. Most of the time the crests are out of step and the sea is merely appalling. Occasionally, briefly, crests from 2 or 3 trains arrive at the same point at the same moment and add together. Superposition. For a few minutes, in one small patch of ocean, you get a single wave of up to 18 meters, 60 feet, where the surrounding sea is running 8. And because that mountain of water is traveling into a fast opposing current, it does not have the shape of an ordinary wave. The forward face steepens until the crest is on the point of breaking. And ahead of it, on the side the ship is approaching from, there is a long, abnormally deep trough. The water sucked down and drawn out by the combination of wave trains fighting the current. Sailors on this coast called it a hole in the sea, and Mallory used their phrase in a scientific paper because there is no better description. This is where the physics stops being interesting and starts killing people. Understand what a ship actually experiences, because it is not what most people imagine. A vessel in a heavy but normal sea rises to each wave. Bow goes up, water comes over the foredeck, bow comes down. Unpleasant, exhausting, survivable. Ships are designed for it. What happens at a hole in the sea is different in kind. The ship's bow drops into a trough that is longer than the ship is. She is not riding over a wave. She is steaming downhill, and gravity is adding to her speed as she goes. At the bottom of that slope, a near vertical wall of water 18 meters high is coming at her at up to 30 knots, 15 meters every second. There is no time for the forepart to lift. Mallory was blunt about it. Under those circumstances, nothing can be done to help the ship. The bow buries itself into the face of the wave. The wave becomes unstable, and hundreds of tons of green water collapse onto the foredeck. Typically, in the reports he collected, striking around 30 meters aft of the stem, right at the break between number 1 and number 2 hatches. And then comes the part that actually breaks ships. The forepeak and chain locker up in the bow are empty spaces. They are buoyant. They want to come up. So the very front of the vessel is straining upward, while a colossal weight of water is pressing down immediately behind it. The hull is being levered across a single point, and that point is the bulkhead between the first 2 holds. The deck buckles. Internal structural members displace. Frames that have never been loaded that way in that direction give. That is why the damage photographs from this coast all look the same. It is why the Wilstar's bow ended up folded down like something soft. It is why one British cargo liner came into Durban with the point of her bow bent under her, hanging beneath the line of her own bottom. It is why more than one ship simply came apart across the forward third of her length. And here is the detail that answers the question this whole story is built around. Look at the wind speeds in these cases. Force 8, 9, sometimes 10. Bad, but not unsurvivable. Not once in a lifetime. Ships work in force 9 all over the world without losing their bows. The reason it happens here is that the wave you meet was not built by the wind you are standing in. It was built 1,000 miles away, sharpened by a shallow bank, compressed by an opposing current, and then stacked on top of 2 other wave trains for about as long as it takes to cross a deck. By the time it reaches you, the local weather has almost nothing to do with it. Now watch it happen to a ship whose officers did everything right. In late September 1973, the machine ran through its full sequence in front of witnesses, with 3 separate ships keeping written logs, and one of them got hit. It is one of the best documented rogue wave encounters on record, and it happened because 2 masters had agreed to write things down. Start on the 21st of September. A cold front is moving east along the southeast coast, having just passed East London. Behind it, fresh southwesterly winds are blowing with a fetch of 1,200 miles, all the way back to around 45 degrees south and 10 degrees east, deep in the Southern Ocean. The gun is being loaded. On the 22nd, the front has run north past Lourenço Marques, and strong southwesterly winds are still blowing along the coast with 800 or 900 miles of fetch behind them. That morning at 8, the motor vessel City of London sailed from Durban for Cape Town. Her master was one of 5 Ellerman and Bucknall shipmasters who had agreed, at the request of their managing director, to send in detailed weather reports whenever conditions on the southeast coast looked capable of producing abnormal waves. It was a voluntary monitoring scheme with no funding and no authority behind it, and it produced some of the most useful data anyone had. Her log reads like a man watching something build. 8 in the morning, south-southwest force 6, rough head sea, moderate swell. 10, southwest 6, noon, off North Sand Bluff, southwest 6, rough sea, short steep swell. 2 in the afternoon, southwest 7. Note that phrase repeating, short steep swell. That is the current shortening the wavelength, written into a logbook by a man who could see it happening over the bow. Sea temperature is worth watching in that log too. It swings from 21.7 degrees down to 17.4 and back up again within a few hours, which is the signature of a ship crossing between upwelled shelf water and the warm core of the Agulhas current. The temperature gauge is effectively telling him which side of the boundary he is on. By 4 in the morning on the 23rd, off Great Fish Point, the wind was moderating. The sea calmed. The heavy southwesterly swell did not. It kept rolling in, generated by another gale that was still hundreds of miles away, approaching the southwestern cape. That is the part of this coast that catches people. The wind can drop to nothing, and the swell keeps arriving, because the swell was never local in the first place. The critical detail about the City of London is where she was. Her entire passage from Durban to Seal Point was on or inside the 50-fathom line, inside 100 meters of water, well in on the shelf. She had no trouble at all. Behind her, a second cold front was crossing the southwestern Cape. By the 24th, it had almost reached Port Elizabeth, with the wind switching from northeast to southwest ahead of it. And on that afternoon, a small research vessel was working the same water and keeping her own log. The Thomas B. Davy was a University of Cape Town research ship, 97 feet overall, on a geological sampling cruise along the continental margin. 97 feet is not much. She was there to take bottom samples, which means she needed to be in specific places at specific depths, and her scientists wanted samples from outside the shelf edge. At 2 in the afternoon on the 24th, she was at 32 degrees 2 minutes south, 29 degrees 24 east, with a northeast wind force 6. Classic prefrontal conditions. Northeast wind spinning up the current and piling water onto the shelf edge. At 5 in the afternoon, the wind was still northeast, force 5, with a heavy southwesterly swell already running underneath it, the swell from a storm she could not see. At 8 in the evening, the wind had eased to east force 4. At 11 at night, it was blowing southwest force 8. There it is. The 4-hour flip Mallory described, recorded in real time, by a 97-foot ship sitting in the middle of it. Northeast force 5 to southwest force 8 in the space of a few hours. The barometer, which had bottomed out at 1005.5 millibars, started climbing. She spent the small hours steaming slowly southwest into force 8 until 2 in the morning when she was 2 miles off Mazeppa Point. Then, because the wind had come down slightly to force 7, her master edged her out on a southeasterly course across the shelf, out past the 100-fathom line, so the scientists could see whether bottom sampling was possible. He got about as far as the shelf edge before he turned round. The log entry is understated in the way that logbooks are, and it is one of the most important sentences in the whole body of evidence about this coast. On crossing the edge of the shelf, the seas became even higher. At 5 in the morning, he put the helm over and came back inside the 100-fathom line, and the research work carried on there. A 97-foot boat crossed one bathymetric contour, and the sea got measurably worse. Not gradually, on crossing. That is the current core, and it has an edge you can feel. By noon on the 25th, she was 7 miles south of Cape Morgan, with the wind at force 9. At 5 in the afternoon, with Hood Point Lighthouse bearing 275 degrees at 10 miles, the wind was force 10. Her master logged high seas and mountainous swell and estimated the waves at 20 to 25 feet, 6 to 8 meters. At 1647 that same afternoon, barely a dozen miles further offshore from the Thomas B. Davy, in the same water, off the same lighthouse, a ship 1,000 times her tonnage was finding out what happens outside the line. The Svealand was a Swedish ore-oil carrier of 258,000 tons, 338 meters long, 1,100 feet of hull, fully laden, drawing 22 meters. She was on her maiden voyage. Think about that draft for a moment because it is going to matter. 22 meters, 72 feet of ship under the waterline. There are stretches of the Agulhas bank where she would have had less than 40 meters of clearance beneath her keel. There are inshore routes on this coast that she physically could not use. She had been in gale-force southwesterly winds since the early hours of the 25th, with waves reported at 9 to 12 meters. Her officers were doing the correct thing and had been doing it for hours. She had reduced speed. At the moment of the encounter, she was making 3 knots. 3 knots. That is barely steerage way on a ship that size. It is the maritime equivalent of crawling. Nobody on that bridge was being cavalier. They had a fully loaded 250,000-ton ship in a force 9 to 10 gale, and they had slowed her right down to protect the hull. Her position was 23 miles from Hood Point Light, bearing 85 degrees. 1 mile outside the 100-fathom line. 1 mile. At 1647, a long, deep trough opened in front of her, and the forward part of the ship went down into it. Before the bow could lift, the wave came down, not over the bow, down onto the deck. It struck the first two hatches and drove them bodily down by 2 feet, opening them up. 2 crew were injured. The wind at that moment was southwest, force 9 to 10. Look closely at that damage because it is precise and it is the signature. The first 2 hatch covers of a 338-meter ship pushed down 2 feet into the hull and split open. That is the levering action. Buoyant forepeak straining up, hundreds of tons of water crashing down 30 meters aft of the stem, and the structure in between failing. Exactly where Mallory said it fails, on exactly the kind of ship he said it happens to. 1 mile outside exactly the contour he identified. She put about and made for Durban. Now hold the 3 vessels side by side, because this is the cleanest natural experiment anyone could ask for. The City of London. Inside the 50-fathom line, force 6 to 7, rough seas, short steep swell, no damage, arrived normally. The Thomas B. Davy, 97 feet long, force 8 to 10, out to the 100-fathom line and immediately back inside it, no damage. The Svealand, 258,000 tons, brand new, at 3 knots, 1 mile outside the 100-fathom line. Hatches driven into the deck and 2 men hurt. The difference was not the ship. It was not the weather. It was not the seamanship. The Svealand's officers were doing everything the Thomas B. Davy's master was doing, on a far stronger vessel, at a fraction of the speed. The difference was a line on a chart. And this is the reversal that changes how you have to think about the entire coast. The Svealand was not unlucky in a general sense. She was in a particular place, and the place is what did it. The danger is not distributed across this ocean. It is concentrated in a strip a few miles wide, running for hundreds of kilometers along a depth contour, and you can steam through the middle of a gale on one side of it and take permanent structural damage on the other. There is one more thing to say about that line, and it is the part that makes the advice harder than it sounds. In September 1973, there was no satellite navigation. A ship fixed her position by radar ranges and visual bearings off charted objects. In the Svealand's case, a bearing and a distance from Hood Point Light. Corrected by dead reckoning between fixes, and checked against the echo sounder where the water was shallow enough to be useful. That is good navigation, and it is accurate to a mile or so on a clear day with a good radar and a known landmark. A mile or so. The Svealand was 1 mile outside the contour. On the information available to her officers at that moment, 1 mile outside and 1 mile inside were not reliably distinguishable. They were being asked to keep 1,100 feet of loaded hull on the correct side of an invisible line in the water, in a gale, in failing afternoon light using a radar range off a lighthouse, when the penalty for being on the wrong side by a mile was structural failure. Satellite navigation fixed that particular problem completely, and it is one of the genuine, unambiguous safety improvements of the last 50 years. A modern bridge knows which side of the 200-meter line it is on to within a few meters, continuously. With the contour drawn on the display in front of the officer of the watch, which makes what happened 50 years later even harder to explain away. That should be the end of the story. Identify the strip, avoid the strip, problem solved. Except the Svealand was there for a reason, and the reason is the same reason ships are still out there today. On the 6th of June 1967, Egypt closed the Suez Canal. It stayed closed for 8 years until the 5th of June 1975. That single geopolitical fact rewrote the map of world shipping and pointed an enormous amount of it directly at the southern tip of Africa. A tanker running crude from the Persian Gulf to Europe suddenly had to add something in the order of 8,000 to 10,000 nautical miles to the voyage, adding 40 to 50% to the transit time. The industry's answer was not to run more ships. It was to build bigger ones. If the voyage is going to be enormously longer, the only way to keep the economics standing up is to move far more cargo per hull. So the yards began turning out very large crude carriers above 200,000 deadweight tons, optimized for a route that goes around the Cape. The Svealand, at 258,000 tons on her maiden voyage in 1973, was a product of exactly that decision. And here is the trap inside the solution. Those ships were built so large, so specifically for the Cape route, that when Suez reopened in 1975, most of them could no longer fit through it. The largest crude carriers went on routing around South Africa afterwards regardless. A temporary political closure produced a permanent class of ship that had no choice but to keep using the dangerous road. Now put that against the geography. Mallory's advice, when he published it, was clear and practical. On this coast, when you are heading southwest with a falling barometer and a fresh northeasterly wind, and strong southwesterlies are forecast in the next 12 hours, get inshore of the 200-meter line before the wind changes and stay there until the sea moderates. Look at what that instruction asks of a fully laden 258,000-ton ship, drawing 22 meters. Inshore of the 200-meter line means shallower water. It means the bank and the rocks on it, and a coastline that offers essentially no harbor capable of taking a ship that size along hundreds of miles of it. It means for a laden tanker moving toward the exact shore that regulations and prudence say a loaded tanker should stay well clear of. Because a grounded tanker is a national disaster, and everyone involved knows it. Mallory acknowledged that directly. Vessels required by the nature of their cargo to keep a specified distance off the coast should instead go the other way, not less than 20 miles seaward of the shelf edge, is Kialomol Mefri in Sorahautend, out beyond the influence of the current core entirely, and only alter course back in when past Great Fish Point. So a big loaded tanker on this coast in a southwester has two options: squeeze inshore over a shallow shelf with a rock-strewn bottom and no refuge, or run 20-plus miles out to sea and give up the current. What she must not do is the intuitive, economical, obvious thing, which is to follow the fast water along the shelf edge. That fast water is worth 4 or 5 knots. On a voyage of 11,000 miles, 4 knots is days. Days are fuel, charter hire, delivery windows, and money. Nobody has to be reckless for the pressure to work. It is built into the arithmetic of the trade. Every escape route on this coast is the other hazard. That is the trap in one sentence. And you can watch it catch ship after ship in the space of 6 years. Start with the 13th of June, 1968. The tanker World Glory, a little over 220 meters long, was carrying 334,043 barrels of Kuwaiti crude, bound for Huelva in Spain. She was about 65 miles east-northeast of Durban. The conditions on record are, again, the same recipe. Southwesterly gale force winds, overcast, heavy swell, poor visibility. She was struck by waves that were estimated afterwards at around 70 feet, a little over 20 meters. At 3 in the afternoon, she broke up. The stern section stayed afloat for roughly 2 hours and then sank. The bow section did not. It stayed up, and the Agulhas current took it, carrying it southwest along the coast. A floating half-ship, drifting with the same current that had helped destroy it for around 40 miles, before it went down near 30 degrees 6 minutes south, 31 degrees 54 east. 10 of her 34 crew survived. The rest did not. Some sources give slightly different crew figures. The National Oceanic and Atmospheric Administration's incident record gives 34 aboard and 10 survivors, and that is the figure to work from. Her cargo went into the Indian Ocean, around 14 million gallons of crude. The port captain of Durban ran the response. Dispersants were organized through the fisheries and industry departments, and the operation ran about 20 days at a cost of roughly $420,000 in the money of the time. Wildlife impacts were reported as minimal, which had more to do with where the wind put the oil than with anything anyone did. The World Glory adds something the Svealand did not. The Svealand was damaged. The World Glory was destroyed. Same coast, same season, same wind direction, and the difference between structural damage and a ship in two pieces with 24 men dead is a matter of exactly where and how the water lands. Less than 2 months later, on the 5th of August 1968, the SS Esso Lancashire was off Durban and ran into one as well. The account of that encounter contains a detail that tells you more about these waves than any amount of theory. The ship had been working through seas running around 20 feet. Then, she entered one wave, and the water passed unbroken over her Monkey Island. The Monkey Island is the open platform on top of the wheelhouse. On a tanker of that period, it is roughly 60 feet above the waterline. The wave did not break over it in spray. It passed over it, still a solid body of water, and it struck well above the trough. And the officers noted that the wavelength approaching the big one was much shorter than the waves preceding it. That is the compression signature, seen from the bridge by people standing in it. The waves ahead of the killer get shorter. It is the current squeezing them together, and it is one of the very few pieces of visual warning this phenomenon ever gives, and it lasts seconds. Then the early hours of the 3rd of May, 1973. The Bencruachan was a British cargo liner, 542 feet, and she was steering 236 degrees southwest down the coast at 20 knots at an even draft of about 30 feet. 20 knots is a serious speed for that hull. She was steaming into head seas while running with the Agulhas current beneath her, and the current on that stretch can be doing 4 or 5 knots in the same direction she is going. Add that up. 20 knots of ship, plus 4 or 5 knots of current carrying her along, meeting a wave train coming the other way. The closing speed between her bow and the face of an oncoming wave was enormous, and the trough that opened in front of her did what troughs do here. The wave, in the words of Captain Di Davies of Smit Marine in South Africa, came out of nowhere, hit the bow, and destroyed the whole bow. Destroyed is the correct word. The tip of her bow finished up 15 feet below the level of her own keel, bent down and under, so far that the front of the ship was hanging beneath the line of her bottom. She could not be repaired in Durban with damage like that. At 1 in the afternoon, the Dutch tug Marjan III got a line on her and towed her stern first, because you cannot tow a ship bow first when the bow is folded underneath her, arriving in Durban at 3 in the afternoon. On the 4th of May. She was stabilized and temporarily repaired there, then sent to Rotterdam, where the crushed bow and the corrugated plating behind it were simply cut off and a new section welded on. The bill came to about £1 million. 3 months after that, on the 1st of August 1973, a brand new bulk carrier called the Neptune Sapphire, built that year at Wärtsilä in Turku, was on her maiden voyage from Aarhus to Kobe. In bad weather off the South African coast, she broke in two and lost her forward section entirely. The crew were saved. The after part of her was towed to East London by the Smit International tug Barents Z, a ship built in 1973 on her first voyage, made of modern steel to modern classification rules, came apart. The Svealand was on her maiden voyage too. 2 brand new ships, both first trip, both structurally defeated on the same coast within 2 months of each other. Then, the 17th of May 1974, and the image this story opened with. The Norwegian vessel Wilstar, described in different sources as a tanker and as a bulk carrier, was in the Agulhas current when a wave tore her bulbous bow away and did in excess of $1 million of damage. Her master's account of the sequence is worth having in full, because it is the clearest first-hand description anyone has of what a hole in the sea does to a ship's motion. He reported that the waves had been striking in series of 7s. At the end of one series, the 7th wave failed to materialize. The ship lunged into an extremely deep trough, and that trough was followed by a wave much higher than the seas preceding it. The seventh wave failed to materialize. That is the hole. The wave energy that should have been there had been drawn forward and stacked into the mountain behind it, and the ship, having nothing to rise to, went down the slope with all her momentum and buried her bow in what came next. The analysis afterwards attributed the damage to a combination of the ship's own pitching motion and a steep incoming wave, producing extreme local structural loads. The photograph of what was left, the great bulb at the front of the hull bent down and crumpled like something soft, became the single most reproduced image in the literature on freak waves, and it is still the picture most people have in their heads when they hear the phrase. 6 ships, 6 years. 6. A 250,000-ton ore carrier, a laden crude tanker, a second tanker the sea went straight over the top of, a fast cargo liner, a new bulk carrier, and a Norwegian vessel whose bow ended up as an exhibit. Different owners, different flags, different sizes, different crews. One mechanism, in one strip of water, doing the same thing to all of them. By the end of 1973, there were enough of these to stop being a run of bad luck and start being a question. The man who asked it properly had spent his career in a position to know exactly what he was looking at. J.K. Mallory was a master mariner, a retired captain in the South African Navy, and professor of oceanography at the University of Cape Town. That combination is unusual, and it is why his paper works. He could read a weather chart like a forecaster, a bathymetric chart like a hydrographer, and a ship's log like a man who had kept one. In 1974, he published Abnormal Waves on the Southeast Coast of South Africa in the International Hydrographic Review, Volume 51. It runs about 40 pages. It is one of the earliest serious scientific treatments of what the world would later call rogue waves, and it is unglamorous in a way that modern science writing rarely manages. It is mostly tables, weather maps, and extracts from logbooks. He assembled 11 known cases of ships that had either reported abnormal wave conditions or foundered as a result of storm waves off this coast, spanning 11 years. He noted, and this is important, that the 11 were certainly not all of them. Many other ships must have met these waves and sustained no damage because they had already reduced speed, and there was no particular reason to report an event that had not hurt anybody. The data set is a record of the encounters that went badly, not the encounters that happened. He then did the thing that turns anecdote into evidence. For each of the 11, he pulled the South African Weather Bureau synoptic charts for the days beforehand and tabulated the conditions: wind direction, fetch, the position of the depression, barometric differential, the timing of the cold front relative to the encounter, and the ship's position relative to the shelf edge and to known canyons. The pattern that came out of that table is disciplined enough to be uncomfortable. Of the 11 ships, all but one, a vessel called the Southern Cross, were proceeding southwest. In every single case, the wind had been blowing from the same direction across at least 600 miles of open ocean for 24 hours or more before the encounter, and in most cases across a great deal more than that. In 7 of the cases, the center of the depression driving those winds sat at or near Marion Island, with 1,200 miles of fetch behind it. In the rest, the depression was closer in, 400 to 600 miles off, with 800 miles or so of fetch, still more than enough for a fully developed sea. In the majority of cases, the cold front had passed the position of the encounter 5 hours or more beforehand. In 2 cases, the Esso Lancashire and the Moreton Bay, the front's passage coincided with the wave, and in both of those the fetch was 1,200 miles and the central pressure of the depression was 976 millibars or lower. And of the 10 ships whose positions he could establish, 8 were within 2 or 3 miles outside the edge of the continental shelf. None was inside the 100-fathom line. 4 were close to known submarine canyons cut into the slope, though he was careful to add that the surveys were too thin to say whether the others were as well. The 5 monitoring ships and the Thomas B. Davie, all of which stayed inside that line, recorded very rough seas and heavy swell of up to 8 meters in the same conditions, and not one abnormal wave. That is about as clean a result as observational oceanography gets from an accidental data set. The waves are not random. They have a season, a synoptic signature, a direction of travel, and a depth contour. 2 smaller items from the monitoring scheme deserve a mention because they show what the phenomenon looks like at the edges rather than at the center. The city of Worcester recorded a particularly violent passage between Durban and Port Elizabeth in conditions that fitted the pattern, and came through it without an abnormal wave. A reminder that the recipe produces one of these only occasionally, and that most ships in most gales here simply have a very bad night. And the city of Lancaster logged something odder. Her officers recorded an echo on the radar which, in Mallory's judgment, could well have been an abnormal wave just outside the 100-fathom line, a wave large enough and steep enough to return a radar echo. Radar sees solid objects in rain. It does not, as a rule, paint individual waves. Something out there was standing up far enough above the sea surface to look, on a radar screen, like a target. Nobody was able to confirm what it was, and Mallory did not overstate it. But it sits in the record as the only occasion when one of these things may have been seen coming, and even then, only on a screen, and only by a ship that was not in its path. And the 2 exceptions in that table have explanations rather than excuses. The Southern Cross, the only ship not heading southwest when she was hit, falls outside a pattern that depends entirely on a vessel driving into a compressed sea. The Jagersfontein needed a 976 millibar depression at Marion Island to manufacture winter conditions in December. That is what a real mechanism looks like. Even the outliers obey it. Mallory also wrote down what a mariner should do with that. And his advice has a bleak honesty in it. On the question of avoiding the wave itself once it appears, he was flat. Because these waves occur without warning, there seems to be no way a vessel could be maneuvered to avoid damage if one occurs directly in her track. No maneuver, no response. If it is in front of you, it happens to you. The only thing you can control is whether you are in the strip at all. So, when heading southwest between Richards Bay and Great Fish Point with a falling barometer, a fresh northeasterly blowing and southwesterlies forecast within 12 hours, stand in toward the coast so that when the wind changes, you are already inside the 200-meter line. Stay there until the wind and sea moderate enough to edge out again. And if you are the kind of ship that must keep well off the coast, go the other way. At least 20 miles seaward of the shelf edge, outside the influence of the current core. He added a practical note about traffic separation that most summaries leave out, and it is a small masterpiece of seamanship. Northbound ships on that coast routinely run within 3 or 4 miles of the shore to use the inshore countercurrent, the one that starts flowing east-northeast about 6 hours before a cold front arrives. That is a real advantage for them, and they are not going to give it up, which means southbound ships driven inshore by a southwester have to be careful not to close the coast more than they need to, especially between Durban and the Banshee River Light, because the safest lane is already occupied by ships coming the other way. Picture what that actually describes. 2 streams of shipping, moving in opposite directions in a corridor a few miles wide, in a gale, at night, because the alternative is a strip of water that can fold a bow under a keel. The paper ends with an acknowledgments page thanking a shipping company managing director, a port meteorological officer, the Weather Bureau, and 3 scientists. And then, before the bibliography, a single line, Psalm 107, verses 23 to 31. Anyone who wants to know what a professional mariner thought of what he had just described can go and read it. So the mechanism was identified, published, and circulated in the Standard International Journal for Hydrographic Offices in 1974. Warnings went on to the charts. Modern South African charts and sailing directions carry them. Between Richards Bay and Cape Agulhas, there is a possibility of the rapid formation, within a few tens of minutes, of very big seas, with abnormally high and breaking waves when a sustained southwesterly wind confronts the main current. And specific areas known for abnormal waves of up to 20 meters are marked. Weather routing services warn about it. Every officer working that coast professionally learns it, and ships kept being hit. That is the fact that has to be explained, and the explanation is not stupidity. Knowing where the danger is does not automatically give you the ability to be somewhere else. Mallory's own advice requires you to act 12 hours before the event, on a forecast, in a way that costs you time and puts you in shallower water. It requires the forecast to be right about the timing of a front moving at 25 knots along a coastline. It requires you to have somewhere to go. It requires your draft to permit it, your cargo rules to permit it, and the inshore lane not to be full of northbound traffic. And it requires a master to make a conservative, expensive decision on a day when the sea in front of him looks entirely manageable, because the wave that will hurt him has not been built yet. Forecasting improved enormously after 1974. Satellite imagery, numerical weather prediction, wave models, real-time current mapping from radar altimetry, all of it real, all of it useful. None of it changes the fact that a ship at 10 or 15 knots takes many hours to move out of a strip hundreds of kilometers long, and a cold front crosses that strip in less time than that. A better warning does not create more sea room, which brings the story back to the Cape itself, and to a night when a ship with radar, a working lighthouse barely a mile away, and 130 years of charting behind her, ended up on the rocks at the southern tip of Africa anyway. At 3 in the morning on the 16th of November 1982, an emergency call went out from a Japanese fishing trawler called the Meisho Maru No. 38. She had run aground about 1.5 kilometers west of Cape Agulhas, between the Cape and the little settlement of Suiderstrand. She had 240 tons of tuna in her holds. There was a storm running. She was a working boat doing a working boat's job on one of the richest fishing shelves in the country in November, in weather. Trawlers do not go to sea in good conditions only. A fishing season is a set of days, and the fish do not wait for the barometer. What ran her ashore is the thing that has been running ships ashore here since the Portuguese arrived, and no amount of technology in the wheelhouse changed the underlying geometry. A low, featureless coast with a light on it that tells you exactly where you are, and nothing whatsoever about where you are going. A shallow shelf that gives no warning by depth alone, because it is shallow for 250 kilometers. Rocks in front of it, onshore weather, and a vessel small enough that a strong southerly sea can move her sideways faster than her engine can move her forward. Radar sees a coastline, but a low, flat coast in heavy rain, with sea clutter filling the inner part of the screen, is a poor radar target. Radar tells you where the shore is. It does not tell you what the sea is doing to you. The crew were extremely lucky, and their luck was geographic. She grounded close in, and all 17 of them survived by swimming ashore. Compare that to the 6 survivors of the Arniston, half a mile out, in 1815. The difference is not technology, and it is not seamanship. It is a few hundred meters of distance and the state of the surf on the night. The Meisho Maru never came off. She has sat there ever since, being taken apart by the same swell that put her there. Over the decades, the wreck split in two, and now only the bow section still stands above the water. A set of rusted frames, a short walk from the marker that says you are at the southernmost point of Africa. It is one of the most photographed shipwrecks in South Africa. People pose in front of it. What she proves is narrow and important. The lighthouse fixed the identification problem in 1849. Charts fixed most of the rock problem. Radar fixed the visibility problem, partly. None of them fixed the fundamental arrangement. A very shallow, very wide shelf, exposed to enormous swell, in front of a coast with almost nothing on it and almost nowhere to shelter. And the last piece of that arrangement, the one that decides whether an accident here becomes a body count, is not on the ship at all. It is ashore. And it is thinner than anyone would like. South Africa is responsible for coordinating maritime search and rescue over a region of roughly 27.7 million square kilometers. That number is difficult to hold in your head, so anchor it. The entire continent of Africa is about 30 million square kilometers. South Africa's search and rescue region is very nearly the size of Africa, and almost all of it is water. It runs from the coast out into the South Atlantic, out into the southern Indian Ocean, and south, all the way down to Antarctica. South Africa is one of only 5 countries with search and rescue responsibility over the Antarctic, alongside Argentina, Australia, Chile, and New Zealand. The center that coordinates all of it is the Maritime Rescue Coordination Center in Cape Town, part of the national organization known as SASAR, operating out of a building in the northern suburbs. When a distress signal comes out of the Southern Ocean, that is where it lands. Now think about what coordination actually means over an area that size. It does not mean assets. It means a telephone, a chart, a list of who is where, and the authority to ask them to go. The MRCC does not own a fleet stationed at intervals across the southern Indian Ocean. Nobody does. What it has is the South African Air Force, the Navy, commercial shipping in the area, and the National Sea Rescue Institute. The NSRI is the part that surprises people. It runs more than 50 bases, coastal stations, inland stations on dams, auxiliary stations, and lifeguard units. And it is crewed by over 1,500 volunteers, unpaid, on call around the clock. It is a charity. The organization that answers when something goes wrong along one of the most consistently dangerous coastlines on Earth is funded by donations and staffed by people who leave their jobs and their beds to go and get you. The station that covers Cape Agulhas is Station 30, based at Struisbaai, just east of the Cape. Its area runs from Coin Point in the west to Infanta in the east, and the NSRI's own description of that stretch is blunt. It has the highest concentration of shipwrecks in South Africa. Station 30 grew from a satellite operation in the 1990s to a full station with around 20 active crew. Most of what they do is not shipwrecks. It is medical evacuations, assistance to fishing boats and small craft in difficulty, backing up the lifeguards, and inland call-outs to help other rescue services. An engine failure on a line boat, a diver in trouble, somebody swept off the rocks. That is the real exposure profile of this coast now. The tankers pass. The chukis and the ski boats and the shore anglers are in it. And then some call-outs are not routine at all. On one of them, the crew launched an 8.5-meter rescue boat into a 7-meter swell with the wind gusting at 45 knots. Sit with the proportions of that. An 8.5-meter boat, 7-meter swell. The wave is almost as long as the vessel is. The volunteers going out are entering exactly the same water, in a far smaller hull, as the people they are going to fetch. That is not an unfortunate side effect of sea rescue on this coast. It is the standing condition of it. There is no version of this job where the rescuers are safe and the casualties are not. The call-out log makes the seasonal pattern plain, too. On the 15th of June 2010, midwinter, the season of southwesterly fronts, Rescue 30 launched at 4 minutes past 1 in the morning into a 25-knot onshore southeasterly and 3-meter swells. 1 in the morning, onshore wind. 3-meter swell on a shallow shelf, which is the condition that produces the steepest, most violently breaking water of all, because the shoaling is happening in the last few hundred meters, before the beach. A rescue boat crossing a bar or a surf line in those conditions at night is doing the single most dangerous thing in the entire discipline, and volunteers do it on this coast in winter as a matter of course. The other option is aircraft, and aircraft change everything when they are available. A helicopter converts a rescue from a surface problem into an air problem. It removes the surf, removes the transfer between two moving hulls, and collapses hours of transit into minutes. 22 Squadron of the South African Air Force has worked with the NSRI on maritime rescue for decades and has pulled people off ships, off rocks, and out of the water in conditions no boat could have reached. A helicopter also has a fuel state, a range, a hoist capacity, a crew duty limit, and a hard requirement for somewhere to refuel. It has weather minima. It has a maintenance schedule, and on any given day there is a finite number of airframes serviceable in the country. So here's what a real rescue on this coast looks like, in sequence. And none of these steps are free. Somebody has to recognize there is a problem, and that is not always the moment the problem starts. A signal has to be sent and received, and correctly interpreted as distress rather than a routine call. The MRCC has to work out where the casualty actually is, which depends entirely on the quality of the position the casualty gave. Somebody has to be tasked, which means somebody with authority has to commit an asset and accept the risk of putting a crew into the same weather. That crew has to be found. For a volunteer station, that means people driving to the base. The aircraft or the boat has to be prepared, fueled, and launched. Then it has to travel, and on this coast, the travel is the part that kills. Then it has to find the casualty, which in a big sea with poor visibility is genuinely hard even with a good position. Then it has to get alongside or overhead, which is the most dangerous few minutes for the rescuers. Then people have to be transferred one at a time from a moving deck to a moving boat or a hovering aircraft. And at every stage there is delay, and every delay is measured in a specific physical currency. How long a person can survive in that water, or how long a hull can survive that sea. The single most important number in all of it is distance, and it is the one number technology has barely touched. Satellite communication means a ship in the middle of the southern Indian Ocean can raise Cape Town in seconds. That is an enormous improvement, and it has saved a great many lives. It also creates a specific and cruel new experience. The crew now know that the shore knows. They can hear people trying to help them, and the helicopter is still 400 miles away or grounded, or does not exist. Communication improved by orders of magnitude. Physical rescue distance did not improve at all. That gap is where most of the tragedy on this coast now lives, and on one night in August 1991 on the same coastline, with everything lined up in the right way, that gap closed completely. And 571 people who should statistically have died did not. It is worth going through that night carefully, because it is the strongest evidence anyone has that this system is survivable, and because almost every element that made it work was a piece of luck that will not always be there. The Oceanos was a Greek-owned cruise ship working the South African coastal trade, and on the 3rd of August 1991, she sailed from East London for Durban. Her objective was ordinary to the point of banality: a short coastal cruise, a few hundred miles up the wild coast, passengers aboard for a holiday. Roughly 570 people were on the ship. Passengers, crew, and entertainers. She sailed into 40-knot winds and a 9-meter swell. Note the season and the direction. Early August, winter. The exact months in which southern ocean depressions push furthest north and the southwesterly gales come up this coast one after another. Note the location too. The wild coast between East London and Durban is the narrow shelf, steep slope, fast current strip that Mallory identified as the concentration zone. The Oceanos was sailing into the middle of the machine on the day it was running. She sailed anyway. Passenger ships operate to schedules. Passengers have booked. And a 9-meter swell is not in itself a reason for a ship of that size to stay in port. This was not a reckless decision. It was a normal one, taken in conditions that would have been survivable for the hull she was in. If the hull had been intact, it was not. At around 9:30 that evening, off the Transkei coast, people aboard heard a muffled sound from below, and the ship lost power. What had happened was a failure of a kind that never appears in the brochure. Earlier repair work on the waste disposal system had left a ventilation pipe running through the watertight bulkhead at the after end of the engine room without its non-return valves fitted. A watertight bulkhead with an open pipe through it is not a watertight bulkhead. Under the pounding of the sea, the shell plating in that area burst open, water came in, and it did not stop at the compartment it entered. It went through the pipe. Two things died within minutes: the ship's power and the ship's subdivision, the compartmentation that is the entire basis of a large vessel's survivability. From that moment, the Oceanos was a large steel box, adrift, with the sea inside her and no engines. This is where the story becomes genuinely difficult, and where it matters to say only what is established. Captain Yiannis Avranas and a number of crew members left the ship without alerting the passengers. That is not an allegation from a newspaper. In 1992, a Greek board of inquiry convicted Avranas and 5 other officers of negligence for fleeing the vessel without helping the passengers. Several hundred people were therefore on a sinking ship at night with no power, no announcement, and no functioning chain of command. The reason anyone remembers the Oceanos as anything other than a disaster is a guitarist. Moss Hills was a musician. He was part of the entertainment team, a guitarist, and he had no maritime training and no authority of any kind. He went below to find out what was happening, worked out how bad it was, and with the cruise director Lorraine Betts and other entertainers and crew began doing the job nobody else was doing: getting passengers up, organizing them, and launching lifeboats. Then he went to the bridge. The bridge was empty. Hills found the radio and used it to broadcast a mayday. He kept broadcasting until a ship answered. Understand what that means mechanically. The distress signal that started this rescue was not sent by an officer following a procedure. It was sent by an entertainer who found an unmanned bridge and worked out how to use a radio telephone in a ship without power, listing at night in a 9-meter swell. The recognition step, the first link in every rescue chain, very nearly did not happen at all. Once it did, the machinery moved. The Dutch cargo ship Nederloid Mauritius was in the area and responded, and other merchant vessels closed in. Those ships did the first part of the work, taking people out of lifeboats, which is itself brutally hard in that sea because transferring people from a small boat rising and falling 9 meters onto the side of a cargo ship is a matter of timing the jump. But there were hundreds of people still aboard. The lifeboat capacity was not going to be enough, and the ship was going down by the bow. The rest was going to have to come off by air. Helicopters were tasked from the South African Defense Force, flying from bases including Cape Town and Durban. 16 rescue helicopters were involved over the operation. 13 of them were Pumas. And here is the transit problem in raw form. Durban is over 200 kilometers from the wild coast in one direction, and Cape Town is close to 1,000 in the other. Aircraft had to be readied, crewed, fueled, and flown a long way through the same weather system that was sinking the ship to a position in open sea at night. The hoisting operation happened the following morning. That detail is not a footnote. Daylight is a physical requirement for winching dozens of people off the heaving deck of a listing, powerless ship. The rescue depended on the Oceanos staying afloat long enough for the sun to come up. Nobody could guarantee that, and nobody aboard could do anything to make it more likely. She stayed up. Through the morning of the 4th of August, 9 of those helicopters hoisted 225 people directly off the deck. Divers went down onto the ship to run the hoist point. Passengers went up 1 and 2 at a time on a cable. From a deck that was tilting further as the hours passed, in the downwash of a Puma holding station over a sinking ship in a gale. Moss Hills and Lorraine Betts stayed until the end and were among the last off. Approximately 45 minutes after the final person was lifted, the Oceanos rolled onto her starboard side and sank bow first. Her bow now lies at about 94 meters. All 571 people aboard survived. Nobody died. That is one of the most complete maritime rescues ever performed anywhere, and the people who flew and swam and organized it earned every bit of the reputation it has in South Africa. Now be honest about why it worked, because the lesson is not rescue works. It worked because the ship stayed afloat all night, which was luck. It worked because merchant ships were close enough to respond, which was traffic density, which was luck. It worked because the weather, while severe, stayed inside helicopter operating limits the next morning, which was luck. It worked because the casualty was within helicopter range of 2 major bases with airframes available, which is a function of exactly where on the coast she happened to break. A few hundred miles further out to sea, and the entire air component becomes impossible. And it worked because one man with no training found an empty bridge and a radio. Change any one of those, and the number is not 0. There is one more thing the Oceanos proves, and it cuts against the way people usually tell this story. The sea did not sink her. A 9-meter swell off the wild coast in August is a hard night, not an extraordinary one. What sank her was a pipe through a bulkhead with the valves missing. The environment out there does not need to produce a 60-foot wave to kill you. It only needs to find the one thing on your ship that is not as strong as the paperwork says it is, and then apply pressure to it for a few hours. The Agulhas coast is very, very good at finding that thing. Which brings this to the present, and to a case that should have been nothing at all. At 2:10 on the morning of the 30th of June 2023, a refrigerated cargo ship called the Beluga Reefer finished loading fruit at the fruit terminal in Durban. She was Bahamas flagged, 149 meters long, with 22 Russian crew, all properly qualified. Her voyage was a coastal hop down to Port Elizabeth. A few hundred miles southwest along the same coast, the Svealand had been damaged on almost exactly 50 years earlier, in the same southwesterly front season. At 2:45, the crew were called to stand by for departure. The forecast was not a surprise. It showed a low-pressure system approaching from the southeast, with strong winds and increased swell likely. In more detail, it gave wind of force 5 to 6, occasionally gale force 8, from the southeast veering southwest, with a swell of 3 to 4 meters from the southwest. Nothing about that is dramatic. Force 8 is a gale, and a 3 to 4 meter swell is a normal winter sea state on this coast. A 149-meter ship handles that. The relevant part of the forecast growing up was not the numbers. It was the direction. Southeast veering southwest. The wind was going to swing round in winter on the Agulhas coast. At 4:02, the pilot left the ship. Immediately afterwards, the master gave a specific instruction. All lines correctly stowed, all deck equipment secured for the passage. That order is the whole incident in miniature, and it was the right order. Mooring lines and deck machinery on a forecastle are the most exposed items on any ship. The forecastle is the part that goes down into the trough and comes up under the water. If a line is not stowed and a wire is not secured, then at some point in bad weather, somebody has to go up there and deal with it. And the front of the ship in a head sea is the single worst place on a vessel to be standing. The master was closing that hazard before it opened. At 4:15, the second officer reported the aft lines and machinery stowed and secured. At 4:20, the bosun reported the forward mooring station secure. It was not secure. The bosun had made a decision that anyone who has worked shifts will recognize instantly. He was 52 years old and had been with the company more than 10 years. He had just come off 8 hours of work, from 8 in the evening to 4 in the morning. And that shift came at the end of 8 consecutive days in which his hours had been staggered and shifted away from his normal day pattern to cover loading and discharging. The ordinary seafarer working with him was 46, 8 years with the company, on the same broken pattern. He was exhausted. The lines could be made fast later in the day. He reported the forecastle secure, went below, and went to sleep, intending to come back and finish the job. This is not a story about a lazy man. It is a story about a task deferred by a tired man who fully intended to complete it, in a system where nobody checked. The master handed over to the third officer and turned in. As the ship got out into it, she began to slam, the bow coming down onto the waves hard enough to shake the hull. Slamming is a noise and a shudder that travels through a whole ship, and it woke the master in his cabin. He got up and he acted on it. He instructed the officer of the watch to reduce speed and alter course to ease the motion. Reduced speed. Altered course. This is a master doing textbook heavy weather ship handling twice before anything has gone wrong. Before midday, the second officer took the watch, with the chief officer alongside him. And here is the detail that makes this incident so much worse than a simple storm. The conditions at that handover were clear skies and sunshine. Sunshine. Not a gale howling over the bridge windows. Not spray on the glass. A bright winter day at sea, with the wind and swell increased and waves recorded in the log as in excess of 3 meters from the southeast. 3 meters. On a 149-meter ship, 3 meters is a moderate sea. At 20 to 2 in the afternoon, the chief officer left the bridge and went out on deck to check the temperatures of the refrigerated containers and their securing arrangements. Routine work on a working day in daylight. At about the same time, the bosun and his deck team woke up, had lunch, and got ready to go back to work. At around 1:45, they walked forward to make fast the lines and secure the deck machinery, finishing the job the bosun had deferred 9.5 hours earlier. Nobody on the bridge knew they were going. That is the second failure, and it is the one the investigation was hardest about. The bridge had already been told the forecastle was secure, so the bridge had no reason to expect anyone up there. No access control had been put in place as conditions deteriorated. 4 men walked to the most exposed part of the ship in a rising sea, and the people steering the ship did not know they were on deck. Shortly after they got there, the beluga reefer was struck by a series of large waves that breached the forecastle. The word in the report is series, not one wave. A group of them arriving together on a sunny afternoon in a 3-meter sea. The water swept all 4 men off their feet and threw them into the ship's structure and deck machinery. On a forecastle, that means winches, bitts, fair leads, anchor gear. Heavy steel with hard edges, bolted down and immovable. At 9 minutes to 2, the chief officer, walking forward on his container round, came onto the forecastle and found 2 injured crew members. He raised the alarm. Then he found the other 2 further aft. He had been out on deck himself, at the same time doing routine work, exposed to exactly the same risk, and the only reason the 4 men were found within minutes, rather than at the next muster, is that he happened to walk that way. The master went to the bridge and immediately altered course for the nearest port, Port Alfred. At 2:15, an emergency team led by the chief officer got the injured men into the ship's hospital. Then came the part that connects this directly to everything else in this story. The master requested a medical evacuation by helicopter. A helicopter was not available. He was instructed instead to alter course for East London and steam there. Paramedics boarded the ship on arrival that evening. Read that sequence again. A modern ship on a coastal passage along a developed country with an air force, a national sea rescue organization, and one of the world's largest coordinated search and rescue regions, requested a helicopter for critically injured men and had to steam them to a port instead, arriving that evening. 2 of the 4 crew members died of their injuries. A third was taken to a local hospital for emergency surgery. The 4th was treated on board for minor injuries. Now hold up the physical conditions against the outcome, Kustistisikat Uchisisikir. Because this is the answer to the question this entire story has been building toward. A later scientific reanalysis of the accident, published in the Journal of Marine Science and Engineering, went back through the oceanographic and atmospheric data for that afternoon. What it found is worth stating precisely. The wind speed at the site was about 5.5 meters per second. That is roughly 11 knots, a gentle to moderate breeze, the kind of wind you would describe as pleasant. The locally generated wind sea was under a meter high. The significant wave height peaked at about 3.2 meters, driven almost entirely by a long period swell from the southwest, with a period around 12 seconds. The classic Southern Ocean signature generated thousands of kilometers away, and there was a current running against that swell at roughly 1.3 meters per second, in water influenced by the Agulhas retroflexion system. There is a discrepancy worth flagging. The ship's own log recorded the waves as coming from the southeast, while the reanalysis identifies the dominant energy as long southwesterly swell. Both can be partly true on a day when the wind is veering. A southeasterly wind sea sitting on top of a southwesterly ocean swell is precisely the crossing condition that makes this coast dangerous. The point of agreement is more important than the discrepancy. The destructive energy did not come from the wind that was blowing there. The study identified one more thing, and it is the most unsettling detail in this whole account. Just before the accident, the angle between the swell direction and the wind sea direction collapsed. It went from 167 degrees, and the two systems almost opposed, to 9 degrees, effectively aligned. What does that look like from a deck? It looks calmer. Two wave systems crossing at wide angles produce a confused, lumpy, obviously nasty sea. When they line up, the surface becomes visually cleaner and more regular, a single direction of swell instead of a mess. Anyone glancing forward would have read that as conditions improving. It was the opposite. Aligning the two systems sharpened the coherence of the wave groups. It made it far more likely that several crests would arrive in quick succession at the same place, with an opposing current shortening and steepening them the whole time. The sea got tidier and more dangerous simultaneously, and there was no way to see the difference from the forecastle. 11 knots of wind, sunshine, 3 meters of swell, 2 men dead on the deck of a modern ship. None of that is freak. It is the same mechanism that folded the Wilstar's bow, running at a scale so small it does not even look like weather. And it happened in 2023, half a century after Mallory published the explanation, on a ship with a competent master who had already reduced speed, already altered course, and already given the order that would have prevented the whole thing. The Bahamian investigators did something in their report that is quietly devastating. Under a heading for previous similar cases, they listed 2. On the 11th of September 2021, the Belgian-registered tanker Arafura was rounding Cape Horn in heavy weather. A bilge alarm went off in the forecastle store. The chief officer and the bosun went forward to re-secure the anchors. A large wave washed them against the deck gear. Neither survived their injuries. On the 28th of May 2020, the bosun and second officer of the Castillo de Valverde repaired a leak on the fire main on deck, finished at 3 in the afternoon, and went for a coffee. Shortly afterwards, work on deck was suspended because the weather was getting worse. They finished their coffee and went back out to collect their tools. A heavy wave came aboard and washed the bosun over the side. A search and rescue operation was mounted. He was never recovered. 3 ships, 3 continents, the same job, securing something on an exposed deck, and the same outcome. So this is not a South African problem. Water landing on a forecastle kills seafarers everywhere, and it has for as long as there have been forecastles. What the Agulhas coast does is take a hazard that exists globally and concentrate it. More energy arriving from further away, focused by shallower water and squeezed by a faster current than almost anywhere else a merchant ship regularly goes, which raises the obvious question. If these waves are real, measurable, and repeatable, why were ships still being designed as though they were not? The answer is that for most of the 20th century, the mathematics said they should not exist. Standard wave statistics treat the sea surface as the sum of a large number of independent components, and that model produces a fairly predictable distribution of wave heights. Under it, a wave more than about twice the significant wave height is extraordinarily rare, and a 25-meter wave is the sort of thing you might expect once in 10,000 years. Naval architects built to that. Ships and offshore structures were designed to withstand a maximum wave height in the region of 15 meters, and mariners kept coming into port, describing 60-foot walls of water with holes in front of them, and being treated, politely, as though they had been frightened. Then, in early 2001, 2 tourist ships got hit inside a week, and one of them had a first officer on the bridge who saw the thing coming. On the 22nd of February 2001, the cruise vessel Bremen had her bridge windows destroyed by an enormous wave. 8 days later, on the 2nd of March, the expedition ship Caledonian Star, a converted 1966 fishing trawler carrying over 100 passengers crossing the Southern Ocean after visiting the Antarctic Peninsula, met one as well. Accounts of exactly where differ. The European Space Agency's account places both incidents in the South Atlantic. Other reports put the Caledonian Star encounter in the Drake Passage. What is consistent across the accounts is the size and the damage. At 5 in the morning, First Officer Goran Person saw a wall of water estimated at around 30 meters bearing down on the ship. 30 meters onto the bridge of a converted trawler. The bridge was flooded, the windows went in, most of the navigation and communication equipment was destroyed. The ship was not crippled, she kept going, but for a period, she was a vessel full of tourists in the Southern Ocean with her instruments smashed and her bridge full of seawater. 2 ships in 8 days with bridge windows knocked in by waves that the design rules of the day said should turn up roughly once every 10,000 years. That was the point where the science moved, and it moved because of satellites. A European project called MaxWave went to the data from the European Space Agency's ERS-1 and ERS-2 satellites. Those spacecraft carried synthetic aperture radar, and among the products they generated were small radar snapshots of the sea surface, imagettes, each covering about 10 kilometers by 5. The MaxWave team took roughly 30,000 of these imagettes, representing about 3 weeks of global coverage, and looked for extreme waves. In 3 weeks of data, they found more than 10 individual waves around the world, over 25 meters high. 10 in 3 weeks, against a statistical expectation of 1 in 10,000 years. The conclusion was unavoidable, and it changed the field. Rogue waves are not freaks of probability. They occur relatively frequently. They associate with ocean currents and weather fronts. And the design standard that ships and offshore platforms had been built to was based on a model of the sea that did not describe the sea. One of the researchers involved put the state of understanding plainly at the time. They knew some of the reasons for rogue waves and not all of them. That remains broadly true today. Notice what MaxWave did and did not do. It confirmed the phenomenon. It gave naval architects and classification societies a reason to revisit their assumptions. It moved rogue waves from sailors' stories into satellite data, which is the currency that gets things changed. It did not put a warning on the bridge of a ship at sea. There is still no operational system anywhere in the world that tells a master, in 11 minutes, 3 miles ahead of you, a 20-meter wave will form. The physics of it happens on a time scale of minutes, in a patch of ocean, a few hundred meters across. You can forecast the conditions that favor it, and South African charts do exactly that. But forecasting the region and the day is not the same as forecasting the wave. Mallory's conclusion from 1974 has not been overturned. If it appears in front of you, there is no maneuver. What has changed is what happens after. Ships are stronger. Bulk carrier and tanker structural rules were substantially tightened over the following decades, in part because of catastrophic bow and hatch cover failures of exactly the kind this coast produces. Hatch covers on the forward holds, the precise component the Svealand had driven 2 feet into her deck, became a specific focus of regulation, with strengthening requirements for the forward part of the ship and for the securing of forecastle fittings. Ships are also better connected. Satellite distress systems mean a vessel in trouble anywhere in the South African search and rescue region can be heard in Cape Town immediately, and ships are, on this coast, better advised than almost anywhere. The abnormal wave warning is printed on the charts. The mechanism is in the sailing directions. Commercial weather routing services will route a ship around the worst of it if the operator pays for the service and the master follows the advice. Every one of those improvements is real. Not one of them changes the 4 things that actually matter out there. The bank is still 250 kilometers wide and 60 meters deep. The current is still running at 4 to 5 knots along the shelf edge, and still turning back on itself south of the Cape. The Southern Ocean is still generating 12-second swell with 1,000 miles of fetch behind it. In winter, every winter. And a helicopter still takes hours to get to you, if there is one. The Beluga reefer proved all 4 in a single afternoon. Her master had the forecast. He had the charts. He acted on the ship's motion by reducing speed and altering course before anything happened. The ship was modern, adequately crewed, and properly certificated. 2 men still died on her forecastle in a 3-meter sea under a clear sky, and the medical evacuation that should have followed did not happen because there was no aircraft to send, which is the uncomfortable through line of the whole thing. Across 200 years, the failures on this coast have moved steadily away from ignorance and toward physics. The Arniston died of not knowing where she was. That problem is solved. The Birkenhead died of an unmapped rock. That problem is solved. The Waratah disappeared, and nobody could say why. That problem is largely solved. We now know what this coast is capable of doing to a ship, even if we will never know what it did to her specifically. The Svealand, the World Glory, the Benkruachin, and the Wilstar died, or nearly died, of a mechanism nobody had assembled yet. That problem is solved too. It was solved by Mallory in a hydrographic journal in 1974. The Beluga reefer's crew died with all of that knowledge available, on a ship doing the right things, because the wave that came aboard was made somewhere they could not see, out of energy that had nothing to do with the weather they were in, and because the only remaining fix, being somewhere else, costs time, money, and sea room that a working ship does not always have. Knowing exactly how a trap works is not the same as being able to step out of it. So the obvious next move is to stop guessing and go and measure it. Put instruments on a ship, send her out into it repeatedly, and record what the sea actually does to a hull. South Africa has exactly the ship for that, and she is named after this stretch of water. The SA Agulhas State is the country's polar supply and research vessel. She runs the relief voyages to the South African bases in Antarctica and on the sub-Antarctic islands, which means that several times a year she departs Cape Town, crosses the Agulhas system, and drives south into the Southern Ocean, into the very belt of latitudes where the swell that batters this coast is generated. The Sound and Vibration Research Group at Stellenbosch University has been instrumenting her for years. Accelerometer channels distributed through the hull, measurement systems recording her structural response, wave observation programs estimating the height and frequency of what she is meeting. Continuous full-scale measurement of a ship's dynamic response in real conditions is genuinely rare. Most of what naval architecture knows comes from model tanks and computer simulation, because putting sensors on a real ship and sailing her into a real gale for years is expensive and inconvenient. There are only a handful of datasets like this in the world. Two findings from that work are worth carrying away. The first is a correction to what people assume a polar research ship does. On a typical Antarctic relief voyage, the Agulhas de Kunaspaken, Eoisas Beavers 2 spends only about 15% of her time in ice. The overwhelming majority of the voyage is spent in open Southern Ocean, in storms and heavy swell. The ice is not the hard part. The water is. The second finding is a number that changes how you picture the whole environment. In those conditions, the researchers recorded high-intensity stern slamming occurring as often as twice per minute. Twice a minute. That is a purpose-built polar vessel, ice-strengthened, modern, being struck hard enough to register as a distinct structural event roughly every 30 seconds, for hours. Everything aboard vibrates. Nobody sleeps properly. Fatigue accumulates in the steel and in the people at the same rate. That is the ordinary background condition of the ocean south of Cape Agulhas, not the disaster, the commute. Which leads to the last question, and it is the one where honesty matters most because it is the one where it is easiest to sound authoritative and be wrong. Is any of this changing? The intuitive answer is yes, and in a specific direction. Climate models have long projected that as global wind belts shift poleward and intensify, the Great Western Boundary Currents, the Gulf Stream, the Kuroshio, the Agulhas, should intensify with them. A faster Agulhas current would mean stronger opposition to incoming swell, sharper wave steepening, and a nastier shelf edge. The observations do not support that, at least not yet. In 2016, Lisa Beale and Shane Ellipott published an analysis in Nature with a conclusion right there in the title, Broadening, Not Strengthening, of the Agulhas Current since the early 1990s. 2 decades of data showed that the current's mean transport had not increased. What had increased was its width and its eddy activity. More meanders, more instability, more energy going into swirls rather than into the main flow. It is a genuinely interesting result, and an unfinished one. It suggests that intensifying winds may be pumping energy into the eddy field of boundary currents, rather than into their mean flow. Other work in the same field points to poleward shifts of these currents, and to more heat being transported into their extensions. Modeling studies have argued for a weakening of the Agulhas current through the 21st century. The literature does not agree, and anyone who tells you confidently that the Agulhas is getting stronger or weaker is ahead of the evidence. What can be said with reasonable confidence is narrower, and it is enough. A broader, more eddy-rich current does not mean a safer one. The mechanism that hurts ships is not the average speed of the current. It is the interaction between wave energy and a sharp horizontal shear in the water beneath it. More eddies means more edges. More places where a swell running one way meets water running another way at a steep gradient. The Beluga reefer was not damaged by the 4 to 5 knot core of the Agulhas current. She was damaged in the retroflexion region by an opposing flow of about 1.3 meters per second, which is less than 3 knots. You do not need the fastest current on the coast. You need the wrong gradient in the wrong place at the wrong hour. Meanwhile, the traffic has gone up, and it has gone up for a reason that should feel very familiar. Since late 2023, attacks on shipping in the Red Sea have pushed a large share of the world's Asia-Europe traffic out of the Suez Canal and back around the Cape of Good Hope. Suez transit volumes have run dramatically below their pre-crisis baseline for years now. And into 2026, they remain far short of a full recovery, with major carriers keeping the African route as their default and industry expectations of continued diversion. Each of those voyages adds a week or two to the passage. Set that against 1967, and the shape of it is unmistakable. A political crisis closes a canal. Traffic routes around Africa. The route is longer, so the economics push toward larger ships and tighter schedules. And every one of those hulls passes across the Agulhas bank, along the shelf edge, through the retroflexion, in whatever season it happens to be. The mechanism did not need to change. The world simply sent it more ships. So put the whole system in one line, because this is what the title of this story actually resolves to. The geography sets it up. A continental shelf that stays 60 meters deep for 250 kilometers, in front of a coastline so low and featureless that for centuries ships could not identify it, ending at a point where the largest current in the region turns around and sheds rotating pieces of itself into the Atlantic. The Southern Ocean supplies the energy, an unbroken belt of storms circling Antarctica, generating 12-second swell with 1,000 miles of fetch, which crosses the intervening ocean at 35 knots and arrives on this coast under clear skies. The weather triggers it, a cold front, moving up the coast at 25 knots, flipping the wind from northeast to southwest in about 4 hours, after a day of northeasterlies has already accelerated the current and piled water up at the shelf edge. The water does the work. The swell shoals over the bank and steepens. The current shortens its wavelength and raises its height. The wave trains run through each other and, for a few minutes in one patch of ocean, they add. Human motive puts people there. The current is worth 4 knots. The Cape route is the only way round Africa. The fish are on the bank. The schedule is the schedule. And a canal closure 10,000 kilometers away can push a large share of world trade past your door. Technology changes what people attempt. Engines that let ships hold a course into weather that sail could not. Hulls big enough to span a wave. Radar that shows a coast but not a sea. Satellites that carry a distress call in seconds. And distance decides the ending. A search and rescue region very nearly the size of Africa. A volunteer lifeboat service. A finite number of helicopters. And a physical transit time that has barely changed since 1991. Every element of that has been documented, measured, published, and charted. None of it is hidden. That is the part that should sit badly. This is not a mystery anymore. It is a known machine with known inputs, and ships still cross it every day of the year because there is no other road. Go and stand at the southern tip of Africa, and you can see the whole thing at once, which is the strangest part. The marker is there, with its 2 ocean names on it. The lighthouse from 1849 is behind you, still working, still throwing its flash out over water that has not been made 1 degree safer by it. Somewhere out in front, past the horizon, the shelf runs on for another 250 kilometers before it drops away, and the current is out there turning. And a short walk west along the shore, at low tide, there is a set of rusted steel frames standing out of the surf. What is left of the Meisho Maru No. 38? The bow section, which is all that remains since the wreck split in 2. 17 men swam ashore from that hull on a November morning in 1982, and every one of them lived. And the boat has been sitting there ever since, coming apart at the rate of about 1 storm at a time. Behind it, a long swell that started somewhere south of Marion Island 4 days ago feels the bank, stands up, and begins to break. And further out, past the surf line and past the reef, with 250 kilometers of shallow bank still running away south beneath her, a loaded ship's lights move steadily west, holding her course on time.